right, AP Chem Scholars, here we are at the end of Unit 5. Section 11 has to do with catalysis, okay, the process of catalyzing a reaction. We've talked about the idea that catalysts speed up a reaction by altering the mechanism in order to lower the activation energy. If there's less activation energy needed, then more collisions are going to be successful collisions. We're going to increase the frequency of positive collisions. Keep in mind, catalysts are never lost. We've talked about this. You may put them in as a reactant, but you get them out in a subsequent step. Okay, so if I start with 10 grams of palladium, I end with 10 grams of palladium. That is definitely how that catalyst would work. And keep in mind that when you add a catalyst, that means that you're going to be increasing the number of steps of a mechanism, most likely. And if it's a multi-step mechanism, it's possible that it doesn't, but the number of steps is not the issue, and that's where a lot of people make a misconception. It's not about the number of steps, it's about the collisions and how complicated they are. So if the catalyst makes this process easier, makes the collisions more likely to happen, then the reaction is going to be faster. So catalysts increase. How do the catalysts actually work? Okay. First of all, we've talked about the idea that they're going to form a more stable activated complex. We said it's going to have a lower energy, and lower energy means more stable. So, and that means then that the reaction is going to require less energy to happen. But a catalyst might also work just by increasing the collision frequency. Okay. For example, the idea of Mentos and Diet Coke. Okay, the Mentos is there just as a catalyst. Its surface is actually slightly pitted like a golf ball in a way, and that allows the carbon dioxide molecules a place to be attracted to. It helps draw them in, and because they start drawing in, they start combining quickly into bigger pockets of gas, as opposed to little things distributed throughout the soda. So what the Mentos is doing is just helping to bring them together to increase that collision frequency, and improving the orientation of the molecules to increase the number of successful collisions. So sometimes it's just drawing things in, like I've talked about with the my saline solution. That's really not saline, it's really hydrogen peroxide. There's that palladium contact in there. The palladium helps draw the hydrogen peroxide together, which is going to increase the collision frequency. But what it does is it gets pulled onto the surface of the palladium, and that allows other molecules of hydrogen peroxide to come in at better orientations and more likely have a successful collision. I'll explain that more in a moment. So there are two main classes of catalysts: homogeneous, heterogeneous. Okay, homogeneous, we've used that term before, so you should know that obviously we're talking about same, in this case same phase. So if the catalyst is in the same phase as the other reactants, it is a homogeneous catalyst. And if it's not in the same phase, it's heterogeneous. Okay. A lot of time the heterogeneous catalysts are solids and mixed in with liquids, solutions, or gases, but it doesn't have to be that way. But the example we're going to take a look at will definitely be in that mode. So with a heterogeneous catalyst, what we have here is a metal that's helping to attract these two diatomics, okay, hydrogen and chlorine. Okay, so in this case, this was actually titanium. The titanium helps pull the chlorine molecules in, okay, because metal would be attracted to the nonmetals. And so what's going to happen is first of all, it's going to make it easier because they're not wandering as much. The hydrogens can be focused inward on these molecules more, and the orientation of them, there's less chance of it coming in at angles over here or whatever else. There's much more likelihood of them landing on top of this molecule to be able to form two HCl's right away, as opposed to forming one and then another one. So it is definitely going to be a means of speeding up the reaction. When the chlorine is being drawn into the metal, and it's attracted to the surface of the metal, we call that adsorption. Okay, we would say the reactant is adsorbed. Okay, when it is released, Okay, when the products are released, we call that desorption, or say it was desorbed. Okay, yeah, that one's a little weird. Adsorption, that kind of works. Desorbed, I never like that word. But hey, it's not all about me. So let's take a look at a couple questions relating to this idea. All right, so we have two different mechanisms here for the decomposition of ozone into oxygen. What do you think is a faster process, mechanism 1 or mechanism 2? Take a moment, look it over, think about it, and think about why, not just, taking a lucky guess or whatever. Why would 1 be faster than 2 or 2 be faster than 1? All right, so let's talk about it. In mechanism 1, we see that, we have, only 2 steps, 2 elementary steps. That seems pretty good. We have 1 intermediate being formed. In mechanism 2, we have 3 steps. Again, that would seem like it'd be slower because it's 3 steps. We see that we have, excuse me, 2 different intermediates being formed, the NO2 and the oxygen atoms. But we have something going in and coming out at the end. Well, that means we have a catalyst. And what do catalysts do? Catalysts speed up the reaction. So even though it's 3 steps, mechanism 2 is the faster one. Okay, so you've got to think beyond just number of steps. It's not about number of steps. You got to think about the complexity of it, absolutely. But without an energy profile, it's hard to know activation energy issues. So sometimes we have to, really expand our thinking a little bit and think about the, what's in there and what's going on. All right, so here's same idea to an extent. We're given 2 reaction energy profiles. You notice that they're both starting at the same spot, the same reactants. They're both ending at the same spot, same products. So overall, these 2 reactions are the same. Okay, which one is catalyzed? Which one is uncatalyzed? Well, this one should be easy. It's almost insultingly easy. But, at the end of the day, sometimes you got to have a little easy, right? We see that the blue path is much lower energy and is a 2-step process where this is 1 step. Well, catalysts usually add a step. So obviously the fact that it's lower in energy, it has the extra step. The blue path is catalyzed. The red is the slower, uncatalyzed version. All right, so there you have it. Unit 5 is done. Then you have your AP classroom assignment to do, and you have your PPC to bang out. So get on it. All right, let me know if you have any questions. Talk to you soon.